Hi, okay, so we're going to go through most of chapter 14 today. It's Tuesday, April 6th. Chemical engineering thermal. Let's see, so this has to do with liquid and solid liquid phase equilibria. So we had for our mixtures like the K ratio, K1 is Y over X for the vapor liquid equilibria. And that equals gamma 1 P sat 1 over P. Right, so we have this expression x1 gamma 1 P1 sat is this fugacity of 1, and this would be in this, say it's in an alpha phase. Right? So we have an alpha phase F1, and we can also have a beta phase. So the caret means fugacity of a component in a mixture, and the phase is this beta phase. So the beta phase, and if it's at equilibrium, then x1 beta, gamma 1 beta, p1 sat. Right? And these p's are the same. So we had, if we were doing liquid miscibility, then we just have x1 alpha, gamma 1 alpha equals x1 beta, gamma 1 beta. But if we have, that's liquid and with a liquid, but it could be that those two are in equilibrium with a vapor. Say you have water and oil, so salad dressing, and then there's a vapor above it. Right? So it's possible to have two liquid phases in equilibrium with a vapor phase. So then this thing, the fugacity in the vapor phase, that's going to be y times p, y1 times p. So everything is miscible in the vapor phase. So there's just one group of materials, right? So in that case, you have to have like, this is liquid equilibria. If you have liquid vapor equilibria, you have to use this x1 alpha, gamma 1 alpha, p sat 1 equals the same for beta equals y1 times p. So you have to keep the p sats so you can get the vapor part of that thing. So that's when those are all at equilibrium with each other. And then you use whatever program you want to use. You could use Margulis 1 coefficient. You could use the acid base, MAB. You could use a Margulis 2 parameter. You could use a unifac, whatever. You can use any model you want for this gammas, right? So that's kind of the approach. So this gets to be a little involved to do these things, right? This is a picture of, excuse me, the liquid and the liquid vapor, right? Equilibrium. So first example is just get the vapor composition, the pressure, and then the gammas. Right, and use binary system, liquid vapor for two phases, and you have the compositions. So in the alpha phase, the 2 component is a minority. In the beta phase, 1 component is a minority. So another thing is if you have, like for the liquid, say if x1 alpha equals 1, so it's pure alpha, then for a pure component, then gamma 1 alpha also has to equal 1 for a pure component. Okay, that means this whole side is 1. That means the other component, whatever this small deviation from 1 in the beta phase of 1, has to equal 1 over gamma 1 in the beta phase. That's if it's pure, if alpha is pure 1. right? So that's something that you use usually to initiate these things all the way through. So you have like X gamma, alpha, beta. If alpha is pure one, then this is X is one, and then gamma is also one. That means this whole side is one. That means X in the beta phase versus dilute is one over the gamma of the beta phase. Right, so, and then, so here, this is just using, so the first you assume, that's what you assume here, gamma 1 alpha is 1 because the x2, x1, x1 in the alpha phase is almost 1. So the gamma 1 is also almost 1. The next x2 in the beta phase is almost 1. So gamma 2 is also almost 1. Right, so that you do that assumption, usually that'll be a first step in an iteration. And then once you make that assumption, then you can just, and you're given the temperature and the two components, composition. The two components are a binary system. That's 1 and 2. That's the composition. The two, the saturated pressures are given, so you can get the gammas. So the saturated pressures are given. So you're trying to saturated pressures 0.7 for 1, and then times the composition. The gamma 1 alpha is 1, so you can drop that out. So just the composition times the saturated pressure gives y1 times p for component 1 in the alpha phase. So component 1, that's the total of component 1, right? It's pure alpha. So, and then beta phase is no 1, so you just get the pressure from the component 2 from the beta phase, where it's 99%. So the gamma 2 beta is 1 because of the dilution thing, and then you just get y2, and then you sum those two and you get the pressure. Once you have the pressure, then y1 times p, you divide that by the pressure, you get y1. So you have the pressure, overall vapor pressure against these two, even though you don't know what they are. And you get the composition from that. Falls right out. And then once you have the composition and the pressure, then you can get the activity coefficients from basically it's y over the gamma, y over the x times the p sat, right? y2p over x p sat, because the gamma is 1. Gamma 1 alpha is 1, so the gamma 2 alpha you get 19.8, and then gamma 2 beta is 1, so the gamma 1 beta is y1p over x p sat times x for the beta phase, x1 for the beta phase, right? Which is, you got for 0.7, something like that. 0.7 is a saturated pressure, sorry. X1 is 0.01. So that gives 95. Those are two big numbers. That means the things are immiscible, right? It means that if the numbers are so large, so if they're near 1, then you have to do an iteration on this. You could use those gammas back in, and you'd feed those back in as gamma 2 alpha, and then you calculate what gamma 1 alpha is. But because those are so large, you don't need to do any more iterations. Basically, these will come out just these small numbers. So that's a solution for this. For the example 14.1. 14.2, so that wasn't using any model actually, because you were just given the saturated pressures and it's so dilute, you didn't really need to calculate anything. You just use this idea that if you're in a pure component, x is 1, and then if x is 1, gamma has to be 1 too. And then that means for the beta phase, it's in equilibrium with it, because x1 times gamma 1 equals 1. This x2 has to be 1 over the gamma. Right? That's usually a starting condition to do iterations. You assume pure phases. In that case, they're immiscible. This is using a model, though. This is using the Fourier-Huggins model. Okay, so we're just going to take the equations and not worry too much about what they mean. But phi is a volume fraction. And so I went through last time. If you want to know phi1 and you know x1, it's going to be x1 times v1 over x1 v1 plus x2 v2. So this is moles per moles. So the moles times the specific volume, which is volume per mole, gives you volume, right? And then you have the sum of the volumes on the bottom. That gives you the volume fraction, right? So you're given the polymers are 1 gram each. So you take 1 gram. So you take 1 gram divided by the molecular weight, which is 10,000 grams per mole. And that gives you moles. Right? And then you're going to take that number of moles, and calculate the x from the moles of the two components. So it'll be the moles of 1 divided by the moles of 1 plus 2. And then the phi you're going to get from the x's times the volumes. So you have the volumes here. Right, so that's kind of, you can get x and y. Actually, you only need the ratio of phi by x1, so it just calculates that. But you need x also for the prefactor. All right, so phi by x1 would just be v1 divided by x1 v1 plus x2 v2. Right, so it's a little slightly simpler. And then you need the chi, which is given by v1 times these del's. You're given the del's squared, the difference in del's squared. Then you need this r, which is a ratio of the v's, and then you're good to go because you know the temperature in r. So you can get the free energy. So predict the energy of mixing. So you want this energy of mixing. Right? So this is the excess, and this plus the so it's going to be g excess plus ln x1 plus x ln x2. Right, so it's going to be that plus the entropy of mixing. This is going to be the total G of mixing. Okay, so that's the deal here. All right, so this chapter, it's like pretty messy. Like there's a lot of different things flying around, but basically it's kind of teaching you how to plug and play. Like you have these equations, they're complicated. You need to calculate the terms in the equation, and you need to figure out how to use them in an equilibrium situation, trying to find out equilibrium. This case, we're just trying to predict the energy of mixing. Right, so assume that they're immiscible with each other. So in the A phase, the A component in the alpha is 0. And then so that means also that the volume fraction would be 0. And then if the B component is 0, the volume fraction is also 0. But the limit of this volume over, excuse me, over mole, see that the volume divides out, like xi by xi, divided by xi cancels, you just get vi on the top. Xi is 0, but xj is 1, so you get vi over vj for that ratio. And in this equation, it's the ratio. So that ends up being that when you assume infinite dilute, you can still calculate that ratio. It still has a value. Right, so if it's infinite dilute, all right, so then we can calculate the gammas. The gammas are given by this equation 1236. You have ln gamma 1 is that ratio, 1 minus that ratio, which is a volume ratio. V1 over, which the volume ratio is the same thing as R, actually. So R is V2 over V1. This volume ratio is VI over VJ, depending on which I and J you have. So it's either R or 1 over R, right? So anyway, so we can calculate these with the volume ratios. So 0.91 or 1 over that's 1.09. And then the rest of this equation is the volume over RT the volume squared. So it's, if you're looking at the 1 gamma, it's 2 squared. And if you're looking at 2 gamma, it's 1 squared. So that's like the Hildebrandt. That's like the Margulis equation for A12 kind of. Right. So A12 is replaced by the del difference. The difference between this is where likes solubilize likes, and if they're different, this is a big number, so that interferes with that makes a positive contribution to the free energy. Anyway, so this is, you can think of this just plug and play, like here's the plug and there's the play. You get the numbers out, they're big, right? So this is logs, it's going to be exponential to the 18. So it's like 10 to the 8. Right? You have the numbers here, 10 to the 8. So this is like e to the power 18. So it's a huge number. It means they're completely immiscible. Right? That's total immiscibility. So once you have the gammas, once you have the gammas, basically you can say it's immiscible at that point, but you can go to get the compositions, right? I mean, gamma 1, so you take the exponential of that, you get gamma 1, gamma A, gamma B, and then because it's pure phases in the phase, it's in equilibrium with alpha. So x gamma beta gamma b beta xb beta equals 1 because xb is almost 1 and gamma b is almost 1. That means that xa is 1 over gamma a alpha. So you can get the 2 compositions, and there basically is nothing in it. Right. So they don't mix at all. That's the end result of this, which is something we knew from the start, because polymers don't mix unless there's some special chemical interaction going on. All right, so that's that. This was actually, this is where the gammas kind of came from for that. The starting gammas, the 66. Let's see what starting gammas. This was dealt with in chapter 12, the same thing, just to show that they don't mix, show that the gammas are large. Basically, the same thing was done in chapter 12 using this equation. Again, the reason, so the Flory-Huggins would really be, like we had x1 ln x1 plus x2 ln x2, so G of mixing over KT or RT is that business, and then plus chi x1, x2, right? And then chi is proportional to 1 over T. Right. So for Flory-Huggins, you're basically, I mean, Flory-Huggins, the way it's where Flory derived it, divide by the molecular weight here, and then that's it. So this part's Hildebrandt, our Margulis model, where chi is del 1 minus del 2 squared, and then times some constants, and then by T, by KT or RT, and then this part, the equilibrium part, you have this reduction in the entropy by the molecular weights, which makes the entropy go to 0, almost 0. Right, so that's why polymers don't mix, because dividing by n gets rid of the part. This is the negative part, like ln of something smaller, 1's negative. So this is negative, this is positive. This is delta G of mixing is positive, it doesn't mix. Right, so because you divide the negative part by n, the thing goes away. That's the basis of these equations, right? But this is a little bit kind of manipulated to get the volume fraction in there. All right, so if you, this is looking at the Margulis, like a 1 parameter, basically the same thing like Flory-Huggins without the n's. So that's the Margulis, and this is A12, right? So, or it could be the dells if you talk about the Hildebrandt. So, so basically for this, you have like 3 components to the, if you want to just talk about the, not the change in mixing, but the total energy. Like, so that you have the change plus this term, the sum of the components times each of their components, like energy of formation, right? Which is, that's just going to be a trend line. So if you look at the composition, that sum of xi times gi over t is just a straight line, right? Because gi is just the component Gibbs free energies. So those are fixed numbers. This is just linear in x. So you want the total free energy for a system that's mixed. It's got this constant contribution going from pure 1 to pure 2, or pure 2 to pure 1. Right? This is x1 at the x-axis. And then added to that, you have this negative contribution, which is this entropy of mixing, x1 ln x1 term, because x is smaller than 1, so ln is smaller than 1's negative, so that's negative. Then you have this positive contribution that's leading to demixing, right? And that's this gamma term, the activity part, right? If you add those all three together, then you get this kind of curve. And these are different temperatures, because A12, so A12 is this average energy times the coordination number divided by RT, right? So as temperature goes up, A12 changes. So A12 is like just the temperature on a different scale, an energy scale based on the average energy, right? So what happens is if you have this free energy, you can think about it as a measure of will something happen or not. So you have a composition here that you throw in your sample, you mix it up, it's 60% 1. So you go and you're on this temperature, A12 equals 1. So when A is low, that's a high temperature, right? Because A is 1 over temperature. So this is a high temperature, it's miscible. So what happens in a miscible state when you're at 60%? The thermal fluctuations of composition leads to deviations from the 60 up and down. So if you make a down composition fluctuation, so if you say like the density goes up and down, if you make an up one somewhere, you have to make a down one to compensate it, so you get the average the same, right? So you have to have equal ups and downs. So you fluctuate from this up and down from 60, you find out that it's steeper going up than it is going down. That means your overall free energy rose because you have more up than down. So it became more positive, right? So that's bad. You increase the free energy on mixing, on demixing. So then you stay mixed. So this looks like a smile. So smile means you stay demixed, right? And then if you have a frown like the top one, so you go up to 60, well, the down steeper than the up. So that means that demixing will be favored. It's going to be favored until you reach a smile. So there's a smile here, smile there. Those are going to be the phases in our equilibrium. The slope at that point is the chemical potential. So the change in Gibbs free energy with respect to moles of 1 is the slope of this. And the chemical potential at that point, E, is equal to the chemical potential at that point, F. And those are the two phases that are in equilibrium with each other. Right? So you go from a single mixture, not demixed, and then as you lower the temperature, so A gets larger, you get to this, the phase separates, right? And these 2 points, those two compositions, so you could plot this temperature is 1 over A12 versus composition. So you're cooling it down, and then you're going to get these 2 points. So you have 2 phase, then you have 1 phase, right? And this is liquid. These are all liquids here. Okay, so as you raise the temperature, though, there's a magic temperature here of kind of 1/2 on this A2 scale, or A2 equals 2, where the 2 phase disappears. That's called the critical point. That's T critical and X critical, composition critical and temperature critical. And at that point, this thing goes completely flat. So it means changes in the Gibbs free energy will lead to no change in the changes in composition lead to no change in the Gibbs free energy. That means that the thing is just can be any composition. So at the critical point, it's kind of an open game, unknown happens. If you're below if you're above the critical temperature or below on the A scale, you're single phase. If you're above and you get this kind of double minima curve, then it's going to phase separate into those 2 points. If you're in the middle, if you're at the edges, it's still smiley phase. So it's still single phase. So that means that like here, this is all single phase at the edges, and then in the middle, it's 2 phase. Right. So that's how, just showing how this free energy relates to the to the phase diagram if they're tied together. So you can do derivatives of that. So you can calculate this. You can calculate this by looking at tie lines. So if you plot the free energy of mixing, then draw that line. Those 2 points are in equilibria. So you can say what the phase compositions are. This one is using a Margulis model that's symmetric, and this is using the UNIFAC, which is asymmetric, because UNIFAC has 15 parameters in it, and then Margulis acid base has 1 parameter. So the 1 parameter model isn't skewed, symmetric about 50. So you can see the difference between these two. The compositions are kind of similar. This one's 35, that one's 10, and this one's like 90. That one's like 95, 0.95, 0.9. So anyway, these are calculated here. So he says how to calculate these, right? Use the Margulis acid base to estimate water and MEK, binary mutual solubilities. That so it's going to be as a function of temperature, right? So composition, tie lines, 298K in 1 bar. So he gives this, and then mutual solubilities binary are also listed. X1 is 34, 922. This is at 298 in 1 bar. So first thing, just look up the alpha betas in the back of the book, and then calculate A12 by the Margulis. Right, so all these are in the back flap of the book. It's just plug and play, and you get 2.931. So it turns out that 2.931 is the same. See, this thing is all done for. Let's see. This is all done for A12 equals 3. Right, these things are all calculated for A12 equals 3. So, so at least this plot is done for A12 equals 3. So that picture, that plot is going to be in the 2-phase region, the top curve A12 equals 3, and that's going to be a 2-phase composition, right? So this is almost the same number, 2.9. That's why he mentions that. So that's the same as the top 2-phase part of this thing. And then calculate the G. The excess G is this A12. So you have the A12 and you have X1, X2 here. And then the mixing part of this is this Xi, this thing, entropy of ideal mixing, ideal solution. That gives you the change of mixing. So so once you have that, you can plot that versus composition. That shows this plot. Okay, so it's not real, but it basically shows that it's 2-phase, right? And it kind of gives a rough idea what the 2 phases are. Better is to use the UNIFAC. Okay, so the UNIFAC is going to be over here. So let's see, this is 14.3. So UNIFAC is going to involve using Excel, or you could use Aspen or something. Right, so basically we're using Excel because it's Aspen none of the programs work on a Mac. Right? Aspen and ChemCAD don't work on a Mac. So basically you have to have a PC to use those, or Parallels or something. So anyway, so this is liquid-liquid equilibria we're looking at, and we're going to use UNIFAC. So liquid-liquid equilibria is like here. Again, we already looked like the alpha ij are parameters that UNIFAC uses. So there's a tab for them, and then this is the UNIFAC for this system. So that's MEK is this. I'm going to regret doing that. Well, I don't know what I did. So that, oh, I see it. Added a sheet. Delete that. Everything runs like slow. And it's basically because I have QuickTime running. It's like, right, so this is the UNIFAC. I want to make it larger. That's not the plus I wanted. I wanted a little plus. So you can kind of marginally see what's going on. So these are the parameters. Down below are the parameters that it's using in the UNIFAC calculation. And this is the part where you need to operate, right? So let's see, what happened to my molecules now? My molecules disappeared somehow. Oh, because I'm looking at B, on A. So the MEK is this guy here. Right, so it's got a carbonyl, so you say CO, CH3CO, right? It's a methyl carbonyl, like that group. So the carbonyl CH3 is that endpoint, and CO is that one. Then over here you have an ethyl group. So instead of saying ethyl, he's got a methyl and a methylene, right? So CH3, CH2, that's those two. So this MEK is just 1, 1, blank, 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 1. Right, and water, the other component is just water, it's H2O there. This is so common that it's its own. Then when you use this, so you have to set, you can't set, so it's set up for a bunch of different 4 or 5 components, right? So, but these components, you can't set them to 0 because the calculation, it'll mess up the calculation. So you have to set them to some really small number, and 1 e to the minus 20 is the most popular small number here. Set it to 1 e to the minus 20 for the other ones, right? So, and then these other two are your compositions. So right now it's set for 0.5 composition of water, 0.05 and 0.95 for MEK, right? And then the gammas are the next line, 12.202, 1.016. So those are just handwritten over here into this LLE, like 0.5, 12.21, 1.016. Those are just hand pasted in there. The 0, 1, again, like if you want to get 0, it's 23.55. To get 0, you have to put 1 e to the minus 20. You can't put 0 here. So if you want 0, it's going to be 1 e minus 20, right? And then this guy for water would be 1 over here. This is like so slow. And then water would be 1. That should give me like 20 if I did it right. Oh, that gives me the MEK one, 45.744. Right, so if I go back to LLE, that's the bottom one of the table. 45.76, right down here at the bottom. So basically just change the compositions down this line, and then you can get all these. Just be careful when you get to 0, it's going to be 1 e to the minus 20. And then you can fill in all the gammas. Those are using the unifact, right? And then once you have the gammas and you know the x's, then you can calculate the Gibbs free energy of mixing, which is going to be wherever I wrote that. So it's going to be this term plus x ln gamma 1, right, plus x2 ln gamma 2. So these two terms combine to x1 ln gamma 1 x1, right? Because if you sum 2 logs, the argument multiplies, right? So that's what it is, gamma times x1, gamma times x2 in the arguments, and then times x2 times x1. That gives you the mixing Gibbs free energy of mixing. And then you can plot it here, and you can see it's got 2 minima. You can draw a line and find what the minima points are. That gives you the compositions that are in equilibrium. And then the bottom is the plot of the activity. The reason to show that the activity is gamma times x. So it's just showing that the activity in the one phase. So you have the water activity, right? And there's the 2 phases, that phase and that phase. That activity equals the activity in the beta phase. It's like alpha beta for water, then alpha beta for MEK. So at that composition point, the activities are all equal. I mean, for each of the components, the activities are equal. I mean, the chemical potentials are equal, right? So that's just showing that activity issue. So anyway, that's a level of sophistication that you need to know of how to use these. Again, this is group contribution. So you have to pick the groups, like whatever groups you have. Then you have to figure out how to get these kind of complicated Excel sheets to work. But Unifact's the main one. because that can cover, it's already got a lot of parameters and it basically can match anything. For liquid, for phase equilibrium, vapor, liquid, 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 or liquid, liquid, vapor, liquid, liquid, vapor, solid, right? You can do it all. So, so let's say you're going to be calculating like basically activity coefficients doing this. That's showing the same stuff. So if you have, right, so if you don't have pure phases, like totally phase separated, and need to solve equilibria without calculating the Gibbs free energy, then there's a routine to do it. And it involves the K ratios. So you remember like K ratio originally was Y over X because you had a vapor phase and a liquid phase. And here we're going to have K ratios for two liquid phases. So it's going to be like alpha over beta of component one. Right, so it's component one in the alpha phase, component one in the beta phase. There's also component two in the alpha phase. So this is K1, just K1, right? Alpha beta, right? So it's, and then because we had, so the K ratios, because the P sats are equal, so we have two phases, alpha beta, with the same saturated pressure. So we have X1, gamma 1, alpha, P sat 1, and that doesn't have a phase, equals X1 beta, gamma 1 beta, P2 sat. So these P1 sat. So the P1s are the same. So you just end up with X1 gamma 1 equals X1 gamma 1 alpha beta. Right, so this business here, which that's the activity. X times gamma is the activity. So the activities are equal in the two phases. Right. So it means that if you plot X alpha over X beta, you're going to get gamma beta over gamma alpha. So the phases switch when you get the K values. That's the only twist of this. So if you know the gammas, you know the K ratio. So why do you need the K ratio? Well, if you write the mass balance, you have X1 beta, X1 alpha, K1, K2. So that gives you X1 beta times K1 gives you X1 alpha. And then you have X2 alpha. So X1 alpha plus X2 alpha has to equal 1. So that means that that thing has to equal 1. And you can rearrange it. It's only got X1 beta and it is unknown. You get this equation. So there's an equation for X1 beta in terms of the K ratios. And the K ratios just depend on the gammas. And the gammas you get from Unifac or from Margulis 2-parameter, Margulis 1-parameter, the MAB, acid base, whatever function you want. So you go and use your function, get the gammas, then plug it in here and you get the X's. So you can go through this as an iterative routine and then calculate what the equilibrium compositions are. That's kind of the general idea. So you need this equation. This is just the definition of K. Like K is X1 alpha or X1 beta. Right, so if you have a ternary, then it's a little bit more complicated, and you can do it for quaternary and any other number of components that you want. You can work out these equations. So it's just the iteration gets a little messier. Like you have a little bit more to deal with. Basically, here you can solve this by iteration. That's the bottom line, right? Because you have equations for the gammas, so you can calculate the gammas. So this is an iterative, say you do a flash and you have liquid, two liquids together, and you want to know, so flash here means you just dump two liquids into a bucket, and then you want to know what are the compositions of the two phases going to be, right? And then if you know the compositions of the two phases, you can tell the amounts of the two phases. Okay, that might be not so obvious, but say you can do a mass balance on each of the components, like 1 alpha and then 2 alpha. And then if you know how much you put into the bucket of component 1, and then you know 1 beta and 2 beta. So if you know how much, say how much component 1 you put in, it's got to be split between alpha and beta. Then you know that component 1 So you can figure out how much mass went to the alpha and the beta phases. And then, so you know the mass of one, you know the mass of two. You sum those two, you get the mass of alpha, you get the mass of beta, then you know how much alpha and beta volume they take up, or between the two phases. In other words, how much is the alpha phase, like 10%, or is it 50%, or is it 75%? Right. So you can tell which the composition of the phases, I mean the amount of the two phases also from this by a mass balance. So once you know the compositions, you can get the mass balance to get the composition, get the volumes of the two phases. So anyway, the routine is first assume pure. So you have, if you assume pure, beta is pure 1, then alpha, which is in equilibrium with it, has to be that x1 is 1 over gamma 1 alpha. And that's infinite dilution for the alpha phase. The same for the beta phase. So you assume the two are completely immiscible. Then once you have the x's, let's see, and the gammas you're going to get from your program, whatever, UNIFAC, MAB, SSCD. Then you have the x's. Once you have the x's, you can get the, you can calculate the kappa from the gammas that you get from the program using the initial composition. So basically the pure components, and then calculate, use that k function to get the x's, the two k functions, and then this is the other k function, and then with those x's, determine the gammas using your program like UNIFAC. You need a composition, like we were putting in the composition in UNIFAC to get the gammas. And if you have the gammas, you can get the new k's. If you have the k's, you can redo this number 3 to get the x's. Once you have the x's, you can plug it into UNIFAC to get gamma. Once you have the gamma, you get the k. You just repeat that thing around until it doesn't change anymore. It's complicated. Like this gets to be like a brain twister operation, but basically it can be done. Right, so there's one, this is water in any case, the same two that we were looking at before. And then assume MAB, which is the simple, kind of the simple model. And then this SSCED model, right, which is this business down here. So it's got alphas, the acid base, it's got dells, it's got volume, it's got these k parameters. The k calculates through the acid base and the dells. It's like a hodgepodge of MAB and Florey-Huggins mixed together, this SSCED. Right? So it's basically also going to just spit out a gamma, basically just give you a gamma is what you want from it. Right? So I'll show you how to use that one. And then the Margulis acid base is the normal A, B, and volume equation that we used before. Right? So so basically, so you can say, let's see now. So this exponential gamma thing, all right, so we have that ln of gamma 1 for Margulis acid base, A12, that you got from this alpha minus alpha, beta minus beta, then the volume thing. So there's some kind of equation for MAB to get A12. So you have A12 from that equation, and then 1 is going to be x2 squared. So this is just like the Margulis one parameter, right? And then that means that, so if we assume pure x2, so that's 1, then we have gamma 1 equals exponential of A12, right? And then we also have x1, x2, x1 alpha beta. So it's like, say, alpha. Then that equals gamma beta over gamma alpha for 1, right? We have that just because x1 gamma equals x1 gamma. for liquid-liquid equilibria. And then if x1 beta is 1, because you said whatever was 1, you end up with that x1 alpha equals 1 over, and then this guy's 1, that's why those two are 1, right? So x1 alpha is 1 over gamma, then gamma's exponential of this, so you end up with x1 is 1 over exponential of a12, which is what he's got here. So x1 alpha is 1 over exponential whatever, and then x2 beta is also that because it's symmetric, because it's Margulis 1 parameter, so it's symmetric. So this equation might be a little confusing at first, but you have to kind of work through that business to figure out where that came from. So whatever, this is assuming pure components, essentially, with this equation. In other words, the two are pure phases. So then you can get this composition for the phases, and it's small, so that all works out nicely. Like this 0.05 is assumed to be 0. Right, so, but you're going to use this number 0.05 in the next iteration. So you have 0.05 and then 95, right, for the two phases. That's your initial. That's basically based on an assumption of pure. Then once you have those x's, you can plug those into MAB to get gammas. Right? Or you could plug those into unifact to get gammas. You can plug those into whatever you want to get gammas, because gamma is going to just depend on the composition. Right? So, like for unifact, ln of gamma, well, we have it right here. Ln of gammas, or for Margulis, ln of gamma is a12 times x2 squared. So then you can get the gamma from that, right? And once you have the gamma, then your k is the ratio of the gammas. Right, you have 13 to 72.07, so you'll get the ratio. Oh, these are the k. So the gammas, ratio of the gammas, these are the ratios the gammas give the k from these x's. Right, so you get the k's. Then once you have the k's, you plug them in here and get new x's. This is where you start the iteration. So this is initialization. Start the iteration, plug in the k's, get the x's. Boom, boom, got the x's. Then once you have the x's, plug them into this equation to get the gammas. The gammas give you the k's. The gammas give you the k's. See, the k is a ratio of the gammas, and then you just keep iterating that till it doesn't change, and you get the equilibrium composition of the two liquids. This is again like Margulis acid base, Margulis 1 parameter. So these aren't going to be very good numbers. But you can get some numbers that are kind of within ballpark of the thing. So with this other model, so this model down here, so we have calculate K12 with these alphas and dells. K12 doesn't change. Then you plug it in here. You need to get the volume fractions to get the gammas. So you have to convert the mole fraction to volume fraction. And then it's this equation with the K gives you the gamma, right? So it's the same initial assumption. You just calculate the gamma using this equation instead of the Margulis acid base. This one, this K12 is kind of it's a little bit of like a skew factor, right? So you're going to get a little bit better result out of this. It's not just a one parameter fit, right? So this is kind of weighting the two sides to shift the curve from symmetric. Anyway, so then you just do the same thing, calculate the k's as a ratio of the gammas you got from the x's, and use the k's to get the new x's, then use new x's to get new gammas, use the new gammas to get the k's, and then do that over and over until you find out that the composition is almost pure for x1 alpha and almost not 25% for x1 beta. Right, so it's quite a bit different than the other numbers. The other one was 92 and 5%. Right, so they're a lot different. So that's this SSCED. Again, like you don't really need to know, just need to know like you can use these different models to get these things, right? To kind of get a little bit of a feel for the equations. So that was liquid-liquid equilibria doing iteration, and they call it a flash, but basically it's just dump the stuff in a bucket and what phases show up, what are the compositions. So if you have a vapor though, so when would you need a vapor? Well, if you do, they have something called steam distillation where you're distilling the material and just throw some water in with it, right? So why would you do that? So you have some organics you're trying to separate, then you add water, which is immiscible, right? So it's going to be totally immiscible alpha, beta phases. Beta phase is just pure water, but the vapor phase is miscible. So that means that so you consider that you have like molecules up here, and then say 2 organics, and then water, right? So you have waters floating around. Well, if you consider them an ideal gas, like the N is what matters. It doesn't matter what they are. So that N, the extra molecules up here, it's going to drive this thing back into the liquid phase. So you shift the boiling point by putting in water, right? Water crowds up the vapor phase. That's going to push things back into the liquid phase. So by adding steam, you can lower the condensation temperature. The dew point will drop because of adding water in there. So you can demonstrate that by using this equation, which is for liquid vapor equilibria. So you have 3 things. So these are the fugacity, the component I in the alpha phase and the beta phase, and then in the vapor phase, and they're all equal. So you have to keep the p sats here because you want yi times p here. Or you could divide p by p sat in the y term if you wanted. So you'd have xa, x gamma, and then y p by p sat over here, right? So that's kind of how this, how we're looking at this thing. So saying a special case of the blah, blah, blah. So it's immiscible in the liquid phase, and then steam distillation. So these are the Y's, like the vapor phase, when it comes off, is 40% water, and then 60% of these organics in a 2-to-1 ratio, right? And then these are the critical temperatures. So with the critical temperatures, you can calculate the K ratio from the shortcut, like PSAT shortcut method. And then the water one comes from the steam tables. You can get the K ratio by looking up the PSAT on the steam tables. Right? And then it's a 0.1 megapascal, and the temperature is the temperature changes. You're trying to get the dew point, right? So it's just constant pressure. So here, the water in the organic phase is 0, so X water is 1 for the beta phase. So alpha's pure water. I mean, beta is pure water and alpha is pure organic. And then you're looking at the, what you're trying to find is assuming no blah, 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 calculate the maximum temperature, which ensures complete condensation. So it means you want to find the bubble point, because you're talking about complete condensation means to form a pure liquid. What's the first place where you see vapor, right? So that means that's the bubble point, right? And the bubble point happens as sum of y equals 1. You take the composition to be the liquid. So the input composition is liquid, it's X, and then you're trying to find sum of y equals 1. So first thing, you use the K ratios, and then you can calculate the y compositions from that, right? Because the K is going to be y over liquid. you find out that the sum of y isn't 1, right? So at 353 for the p sats, then you just change the temperature until you get that to be 1. Then you can find out what's the composition of the vapor phase that's in equilibrium with that liquid phase to make it into so it's 100% liquid. That's a bubble point. And then the temperature is the temperature you're looking for. So it's 95 degrees C. Right. So adding the organic to the water, even though they're immiscible, made the water boil at a lower temperature. Right. So that's kind of odd. And then the other thing is that the boiling of the first bubble point for the organics has been dropped, right? Because it was 433 and here's 368. So the organics are strongly shifted by having the water present. So you can manipulate the behavior by adding water to a distillation column. It's called steam distillation. Right? So it shifts the equilibrium points. So so that said, let's see. So that's kind of as far as we can get, I think, with this. Right? We're out of time, so I'm gonna have to quit there. So I'll have another class tomorrow, and then I'll go through some problems. So, okay, thanks. I got up to 29. That's